Hello everyone, let us continue our journey in the transport layer with the TCP congestion control. But before we start talking about the TCP congestion control, I'm going to give you some brief introduction about this congestion in the networks and this principle of congestion control. I'm not going to tell you all details about this part, but I'm just going to use 3 or 4 slides in this part. Okay, so informally, the congestion in the network is defined as too many sources sending too much data that is too fast for the network to handle. Okay, and we can see from this illustration. So, for example, let's say there is a highway, and then in the highway there are too many cars going in to this highway, and with the very high rate. So after some time, then the highway will be congested. No cars can move anymore in the highway. So in the same way, if there are too many packets flowing in the network, so after some time the network will be congested. And as we have studied in the first chapter, the cause of this congestion is that there will be packet loss due to buffer overflow in the router, and there will be long delays due to the queuing delay in the buffer of the routers. And then once again, this is a different concept from the flow control, because in flow control, it only deals with one sender and one receiver. But in the congestion control, it involves all the senders in the network, so it is more general. Okay, so I'm just gonna jump to the last part of this part. Okay, so this is the first thing that we have to agree, that we have to understand, like this is the common ground. The first concept is the throughput can never exceed the capacity. So the capacity is like the upper bound in the network. So for example, this is the maximum rate. So when we start sending packet to the network, the throughput starts to increase. But then as the number of packets increases, then and it approaches the maximum capacity. After that, after some time, then we cannot increase the throughput anymore, right? So this lambda is actually the packet arrival rate. And then as the throughput increases, or the actual packet incoming rate increases, the delay is also increased. And when it approaches the maximum capacity, the delay will increase up to the infinity. Oh, well, we have already studied this in the first chapter. Okay, now in the ideal case, due to the packet loss and retransmission, then the actual throughput will decrease. So this dotted lines is the ideal throughput, the maximum, the capacity. But then due to the retransmission and packet loss, then the throughput is decreased to this level. And then the throughput can even more decrease if there is duplicates. As we already studied before, the retransmission and TCP can happen due to the first due to the loss acknowledgement. So due to loss acknowledgement, then the sender retransmits the packet, although the packet is already received by the receiver. And also due to the sender can retransmit due to the late or the parameter timeout. So the actual action is already sent by the receiver, but then it due to the network delays, it arrives late, and then the time is already reached in the sender side. So the sender starts to retransmit the same segment to the receiver. So this even decreases the actual or the effective throughput to this level. So this is from the first from the packet loss and retransmission, and this is due to the duplicate. And the throughput can even more decreased due to the transmission capacity, which is from the packet loss downstream. So this illustration, this can be best illustrated by, let's say, if we have let's say one router, there is sharing several flows, and we have same capacity for the incoming incoming link. So let's say the capacity is R. Okay, so there are two flows that are competing for the throughput or for the rates. Okay, so the maximum throughput for these two links are, let's say, if assuming that they are same, then it should be R half of R, right? But then in reality, let's say for example, flow number 1, it is sending with the higher rate than R half, and then at some point it can go up to go up to R. So in that case, when the flow number 1 sends the packet with the rate higher than R half R, the throughput of the flow number 2 will be decreased lower than half R, and then eventually it can go up to 0, right? So this is what is shown in this graph. Okay, now what we are doing in the congestion control in TCP, this is the one that we will be discussing later. There is no feedback from the networks. This is what we are, pure from the transport layer. So the congestion is inferred from the observed loss and delay, and how the TCP know that there is a congestion. So actually, as what we have already studied before, the TCP can get information about the packet loss. First one is from the timeout. The second one is from the triple duplicate ACK, right? So these are the two important informations that are used for the TCP to infer that there is a congestion in the network. Okay, and the next one is this is called network assisted congestion control. So in this case, for example, when let's say there is data sent by this client, okay, and then X is sent by the server. Let's say it arrives at this router. The router says, the router observes there is a congestion in this network. So when the data is sent to the server, the router will add 1 bit information about the congestion. Okay, there is congestion in this network. Okay, so when the server sends the acknowledgement to the sender or to the client, then the server will add this information back to the segment that is sent from the server to the client. So this is called also explicit congestion control. Okay, now let's go to the actual TCP congestion control. The very basic congestion control approach by TCP is called the AIMD. This stands for additive increase and multiplicative decrease. So why this is called the AIMD? Because the sender can increase the sending rate until it detects there is a packet loss. So if there is a packet loss, it can infer that there is a congestion in the network. Then when it notices that there is packet loss, then it decreases the sending rate, okay, by half. Okay, it can be by half or by by even more numbers. Now let's have a look at this illustration. So let's say we have a time axis, and then this is the TCP sending rate of the sender. Okay. All right. So as we have said before, the sender sending the segment incrementally one by one over time. Let's say at the first time it sends with the, let's say, I don't know, let's say 5 or 10. Then increase the next step, it sends 11 and then 12, and then when it sends 12 segments, it detects there is a packet loss. So then it decreases the window or the congestion window or the sending rate to half. Okay. So then it sends the next transmission. It sends starting from 6, and again, okay, it starts from 6, 7, 8, 9, 10. Let's say until 16. Then when the sender sends 16 segments at the same time, detects there is a packet loss, so it cuts the sending rate to half. Then it starts from 8, 9, 10, 11, 12. There is loss, then it starts again from 6, and so on and so forth. So this is what we call as the relative increase, multiplicative decrease. So if we have a look at this graph, it looks like sawtooth behavior, and it's like probing for the bandwidth. So we are trying to test how much is the available bandwidth in the networks by sending the segments slowly, okay, incrementally, one by one. Now there are different approaches taken by let's say different TCP flavor. We'll discuss later. There are at least the basic one, TCP and the most basic is TCP Tahoe, and the TCP Reno. Okay, in TCP first, let's say TCP Tahoe, when it detects there is any packet loss, then it will start from one MSS or one segment to be sent. Okay, so if we go back to this slide, so in TCP Tahoe, no matter how many segments it sends, let's say when it's detect loss at 12 sending rate, then the next time it will start from 1, okay, and then go up until 16, and then when it detects the packet loss in the 16 sending rate, then it starts from 1 again. Okay, so but for the TCP Reno, it cuts the sending rate to half. Okay, and specifically for triple duplicate X. So okay, so we'll talk about this in more details in the next video. And why AIMD? AIMD is a distributed. This can work in each host. It doesn't need any notification from the networks, and it's asynchronous. Okay, and it's optimized congestion flow rates network wide. So it can work in the networks wide. It can be proven by the simulations and by experiments, and it's quite stable. Okay, it's not giving any problem to the networks. So I think that's it for now. Let's continue with some more congestion control mechanisms in the next video.